Hello. Okay, I'm Shuai, and welcome to the second session today. Our first speaker is Yikai Zhao from Peking University. The paper he's going to present is P4 LRU towards an LRU cache entirely programmable data plan. So after his talk, co-author Kai-Cheng Yang will join for answering questions.
Thank you. Good morning, everyone. My name is Yikai Zhao from Peking University, and beside me is my co-author Kai-Cheng. Today, I'm honored to present our work at the SIGCOMM' conference titled P4 LRU towards an LRU cache entirely in programmable data plan. This work is a collaborative effort between Peking University and Huawei Cloud. In the hierarchical storage structure of computer, media closer to the processor offers superior performance, while upper layer media serves as a cache for the lower layers. Similarly, in network systems, available memory, including that in the switches, also follows this pattern. Given that data packets invariably pass through on-chip memory in the switches, it becomes an appealing proposition to cache content from off-chip memory or remote server memory in this on-chip memory using custom programs in the programmable data plan. This offers significant benefits at a minimal cost. We recognize multiple functions for data plan caching. It can serve as a read-write cache for off-chip memory, providing a faster path. And when acting as a read-write cache for remote memory, it can store or buffer data on the data plane, reducing server load. Cache performance hinges on the replacement strategy. The LRU has proven appropriate in most scenarios. We analyzed two typical LRU algorithms based on time steps and priority queues. However, when trying to implement them in the data plane, both run into the issue of accessing the same memory block twice within one packet's processing, which violates current programmable data plane restrictions. To circumvent this, many works have adopted timeout-based strategies. Another alternative involves approximating the LFU, as retaining the most frequently used entries equates to preserving heavy hitters. Some sketch-based heavy hitter detection algorithms present valuable options for LFU. The last category of solutions sacrifice real-time performance to implement more sophisticated replacement strategies through control loops. And for now, there isn't any work that has realized the LRU algorithm. So compared to a fully associative global LRU cache, we believe that set associative LRU cache deserves more attention. While it provides similar performance, it's notably easier to implement. Upon an analysis of existing LRU algorithms, we identified that the need for multiple accesses to the same data stems from storing keys and values together. This design forces them to sequentially access all entries before circling back to modify a specific one. We discovered that separating the keys and values can eliminate this double access. We designed the P4 LRU, which maintains the keys in LRU order, but never changes the order of the values. Instead, we utilize a cache state to record the current mapping between keys and values. To better understand the P4 LRU, let's illustrate with two examples. Imagine we have 4 keys in the cache, sequentially stored across 4 stages, with their respective values also stored in sequence. Now, if key C arrives, we store key C in the first stage, shift key A to the second stage, shift key B to the third, and identify the key C originally in the third stage. The cache state then transitions to 3, 1, 2, 4, and we know that key C's value is located in the third position. Later, the new key KE arrives. We store KE in the first stage and shift KC, KA, and KB to the second, third, and fourth stages, respectively, while evicting KD from the cache. The cache state transitions to 4, 3, 1, 2, recognizing that KE's value can reuse KD's fourth position. We see that the cache state is a permutation. Adjusting this state is the multiplication of permutations. However, performing performing multiplication of permutations on the current programmable data plane is not feasible because it demands a read register, lookup, read register operation, which isn't yet supported. To overcome this challenge, we propose encoding the cache state as an integer and manipulating the state encoding through stateful ALUs. Given that state transitions are multiplications of permutation groups, we approached this from a theoretical standpoint, assessing which group operations can be encoded into the data plane. First and foremost, the operations of the cyclic group can be trivially encoded. Furthermore, if group H and K can both be encoded, and if group G is the direct product of H and K, or if the quotient group of G over H is isomorphic to K, then G can also be encoded. Okay. Following these premises, we discovered that the operations of permutation groups S2, S3, and S4 can all be encoded. This means that P4 IRU encompassing 2, 3, and 4 entries can be implemented respectively. However, since the subgroup A5 of permutation group S5 is a simple group without any non-trivial normal subgroups, we have yet to find a way to encode it. Nonetheless, we are optimistic that recent advancement in synthesizing state machines in the programmable data plane might shed some light to this issue. Beyond this framework, we have also incorporated heuristic optimizations. For P4 IRU catching 3 entries, we can encode the cache state into 1 integer instead of 2. Coupled with our assigned encoding, apart from multiplications with the identity permutation, the remaining 2 types of multiplications can each be executed through 2 arithmetic logics. As one SLU supports 2 branches, we can implement the entirety of the state transitions with just the 3 SLUs within the same switch stage. After implementing a strict local IRU cache, we have based our set-associated P4 IRU and the tailored 3 network systems for 3 caching functionalities. The first is IRU-Mon, designed specifically for remote read caching. IRU-Mon integrates a sketch-based Morse-flow filter with a P4 IRU-based elephant flow cache. The latter buffers and compresses measurement data, considerably reducing both transmission bandwidth and processing load. IRU-Mon has been deployed in Huawei Cloud traffic billing system to approximate the count of all outgoing traffic at each data center. The combination of sketch and the data plane caching ensures that the system possesses both flexibility and accuracy. The second is IRU table, designed for local read caching. It's a data plane lookup system. IRU table utilizes the P4 IRU to cache table entries, offering a faster path. The third, IRU index, is tailored for remote read caching. It's a distributed database acceleration system. IRU index leverages the P4 IRU to cache data indices, reducing the load on servers. We evaluated the performance of P4 IRU in the 3 network system scenarios through testbed and the simulation. On the testbed, we confirmed that in all 3 scenarios, P4 IRU significantly outperforms direct mapping data plane caching. In the simulation, we compared P4 IRU with algorithms based on time steps and timeout mechanisms, as well as approximate LFU algorithms with the elastic cache and cuckoo cache replacement strategies. The results showed that in all 3 scenarios, P4 IRU consistently maintained a lower cache miss rate. Also, in the simulation, we compared P4 IRU with the ideal IRU cache. The findings revealed that in the 3 scenarios, the set-associated P4 IRU's performance closely approaches that of the fully associative ideal IRU. So, in conclusion, we analyzed why typical IRU algorithms cannot be implemented in data plane and introduced a strict local IRU algorithm, P4 IRU, adapted to the data plane pipeline architecture. We deployed a local P4LRU with 3 entries on the programmable Tofino chip and utilized the multiple techniques to augment cache capacity and performance. Using P4LRU, we constructed 3 practical data plane systems and validated P4LRU's effectiveness by assessing their performance. Thank you all for your attention.
Questions?
Hello, I'm Xiwen from Xiamen University. I would like to ask if P4LRU can cache for variable length key value pairs.
In our design, it currently can only cache fixed length key value. Okay, but I think the ability to cache variable length key value is it's dependent on the design of the value part. For example, we can use multiple stages to store one value, and we can even use loopback or another technique to store a longer value. And I think the main design or the key design of our P4LRU is the technique of separating the keys and values. So I think, in conclusion, I think it can support variable length value. Thank you.
Thank you.
Hi, Nate Foster from Cornell. Really nice talk. I have a very high-level question. So you could imagine caching items in the data plane as you've done. You could also imagine using a programmable switch to interact with some kind of disaggregated storage. Could you talk about the sort of high-level trade-offs and why you think this approach might be, where you think this approach might be more applicable?
Sorry, could you repeat your answer?
Could you contrast caching on a P4 switch versus using a P4 switch to interact intelligently with some fast storage that's remote, like in T or other similar systems?
Okay, I understand the answer. So I think the static memory or SRAM in the switches, it's wait a minute. I think the cache in the switches is faster than the cache in the remote fast memories by using techniques such as RDMA. So I think we can cache the most hottest keys and values in the switch in the switch memory, and the medium hottest key in the remote fast memory, and the least hot key in the like a server memory. So I think these two techniques can use together and simultaneously. Thank you.
It's Rahul from FutureWay. It's a nice talk, and it sounds a smart idea. But in practice, it seems your system currently can only support very few cached items in the system. Do you think that's sufficient for the applications? Isn't that too small for most of the use cases?
In fact, our P4LRU cache unit can only support 2, 3, or 4 items in current, but we can use the set associative cache to enlarge the cache capacity. In fact, we can use almost all the static memory in the Tofino switch, which is about 10 megabytes. Okay.
You mean you will concatenate several of such caches in the system, or?
Yeah, yes.
Okay. Thank you.
Thank you. Very nice question.
So our next speaker is Jiayi Chen from Austin. And Jiayi's main research direction is improving network systems with machine learning. And the paper she's going to present is Darwin, flexible learning-based CDN caching.
Thank you for the introduction. Hi, everyone. I'm excited to present our work, Darwin, flexible learning-based CDN caching. This is joint work with collaborators from UT Austin, UC Berkeley, UMass Amherst, and Akamai. Content delivery networks serve most of the internet traffic today. They deploy numerous edge servers that are close to the users, and each server acts as a cache for faster data retrieval. Effective cache management policy plays an important role in optimizing user performance and reducing the performance costs. However, crafting an effective cache management policy can be very challenging, given the fact that the traffic changes on a CDN cache server. Consider this CDN server that primarily serves download requests of very large objects. Let's say when some breaking news occurs. This server may start additionally serving some web requests because of the increased user demand of related web pages. And these web requests can have much higher request rates. These traffic changes can actually happen very often every day. And this raises this question, are static management policies effective enough? In this work, we focus on the hot object cache omission policy, or HOC. In a common two-level cache server, objects are usually first written to the larger but slower disk cache. And when some HOC omission criteria is met, it will then be omitted to the smaller but faster RAM, or HOC. A common HOC omission policy considers the frequency and size of the object. It omits an object when its frequency is larger than f and its size is smaller than s. An important cache metric that directly reflects the user perceived response is the object hit rate. HOC object hit rate is the number of HOC hits among all the requests. And we've observed that static HOC omission policies fall short when the traffic changes. Our analysis of the image and download traffic subsets of the production server trace shows that an optimal policy for one traffic class can be suboptimal for another, resulting in significant performance drops. Given that there is no one-size-fits-all static policy, we then ask, can we learn the optimal policy for the current traffic? There are some previous attempts at building adaptive omission schemes, but they have some shortcomings. The first one is some of them restrict the policy decision knobs, meaning that changing the set of knobs may need a completely new approach. Adapt size, for example, can only adapt the size threshold. Secondly, these approaches generally cannot accommodate hardware-dependent metrics. For example, the shadow cache-based approaches can only model performance metrics like hit rates, but they cannot model hardware-dependent metrics like disk ops due to the complexity of modeling heterogeneous hardware behaviors. The last issue is the high overhead. RL cache, for example, performs per request inference, which affects the latency. This is where Darwin comes in, a solution that applies generally to any set of knobs, accommodates hardware-dependent metrics with minimal added overhead. Darwin operates on frequency and size-based HOC omission policies. It evaluates the performance of various policies empirically, and then select the best policy for the current traffic for deployment until the traffic pattern changes. And in this process, we have two challenges. The first challenge is the scalability of performance evaluation, and the second is the efficiency of the best policy selection, given this large input space of the policy space. For performance observation, a very straightforward approach is just to sequentially run each policy for some requests, and then observe its performance. However, this method is impractical, given that it takes too many observation rounds and may not converge before the traffic shift. With more resources, we can, of course, parallelize this process and simulate the cache behaviors of all the non-deployed policies with some approaches like shadow caches. but they bring significant compute and memory overhead. Now let's take a closer look at two policies that only differs in their size thresholds. On the same traffic, both policies would emit all the objects with size smaller than 50. In addition, policy J would also emit these blue requests with sizes between 50 and 100. This observation of correlations through shared emissions into the hawk led us to train cross-policy prediction models. These models use traffic features and the policy performance of one policy to decide the policy performance of all the other policies. And we empirically find that the single-layer neural networks are actually effective enough. We also introduced feature clustering and policy association to reduce the starting policy space. We extract the features from the current traffic and then find the closest cluster. Each cluster is paired with some good performing policies for traffic in this cluster. And we only need to explore the corresponding policies of the cluster that our current traffic belongs to, which greatly reduces the number of policies. The second challenge is efficient policy selection. We've developed a variant of the best arm identification problem in the Bennett problem, which we call track and stop with site info. Here's how it works. In each round, we observe the performance of the current deployed policy on a series of requests. And then we feed this observed performance and also the current traffic features into our prediction models. That will give us the other policies' predictions. And then we ask if we're already confident of the best policy. If we're not, then we're deploy the next policy to gather further information. And if we're already confident, we'll just deploy the best policy for future rounds and terminate this policy selection process. We've theoretically proved that convergence time is actually bounded by a constant that is independent of the number of policies. Putting it all together, Darwin trains cross-policy predictors and feature clustering offline, and then during the online process, Darwin first reduces the policy space by feature clustering and policy association, and then we'll run the track and stop algorithm with site info to select the best policy and deploy it until the traffic pattern changes. The cross-policy predictors don't pose any limitations on the decision knobs. And Darwin can take in account of hardware-dependent metrics because these predictors are solely based on the offline observed performances. Cross-policy predictors impose very lightweight predictions only in the first few rounds. And when coupled with our feature clustering, the overhead of the policy is greatly reduced. We evaluated Darwin extensively, both in simulations and an Apache traffic server-based prototype. Our results show that Darwin is robust to traffic changes. On the x-axis is a subset of the baselines that we compare to, and each bar shows the average improvement in Darwin's hawk hit rate compared with this respective baseline. And we can see that Darwin outperforms all the static baselines because no static policy works well for all the traces. For the three adaptive baselines listed here, percentile uses the F and S threshold for their frequency and size threshold. Hill climbing runs two shadow caches with opposite directions of threshold changes for each threshold and moves toward the direction where the performance is better on each update. Adapt size uses Markov chain tuning of a probabilistic site threshold. These methods all require some additional parameters, and they have access to a finer granularity of policies. In this plot, we show the baseline results with their best parameters. Despite these advantages, our Darwin still outperforms all of them. We want to highlight three additional results. Firstly, our cross-policy models are robust in our use case. Secondly, Darwin can be used to improve other metrics. For example, a combination of hit rate and disk ops. Lastly, it doesn't impose additional latency overhead and minimally impacts CPU and memory utilization. Please refer to the paper for more details. To conclude, Darwin can learn the best hawk emission policy and flexibly adapt. Even though in this talk we describe Darwin in the context of hawk emission, we believe that it can be applied to other policy selection problems in network systems. Thank you for your attention, and I'm now open to any questions.
Hi, I'm Venkat Padmanabhan from Microsoft Research India. It's interesting work, but maybe I missed something here. You're trying to predict the performance of certain policies based on a given base policy, right?
Yeah.
But how about predicting what, how the workload might change? Because even the base policy's performance so far may not be reflective of what's going to happen in the future if there is flash crowd or there's some unpredictable, there's some change, right? So how do you deal with that here in this framework?
So this prediction happens in each round. And in each round, we're selecting the policy to gather information, and this selection is controlled by our track and stop with site info algorithm. So what it does is, it is selecting the policy that it thinks it has fewer information and wants to learn more about. And in each round, it will observe the policy performance of this policy, and then use the prediction networks to predict the performance of the others, and then based on this track and stop with site info, we'll decide whether we have enough information for the next round to select a new policy or just deploy the current best policy. Yeah, so these prediction networks are used in each round to gather more information on all the policies instead of just one deployed policy.
Sorry, how long is each round? What's the duration?
Well, in our case, it's, I think, 50,000 requests.
I see. Okay, thank you.
Alexander, ETH, great presentation, thank you. I have a question about the track and stop algorithm. I guess one of the key parts is the confidence, whether it decides that it needs more information or not. Can you give a bit more insight on where this confidence comes from, and does it kind of decay over time, or can you share a bit more?
Yeah,
there?
sure.
Thank you.
As I mentioned, this confidence is actually based on both the deployed policy's observed performance and also on the predicted performance. So this variance could come from both. If in each round, your performance varies in each round, then I would say I'm not really confident on the performances that I've observed. And also, it depends on the predicted performances. For example, I'm predicted based on policy A in the first round, and I'm now predicting the performance based on policy B in the second round, and they show very different performances. Then I'm also not so sure on the policy performances that I've predicted. So we're calculating this confidence based on the variances of your policy predictions and policy deployment.
Okay, let's thank our speaker again. And our next speaker is Rahul Bothra. He's a first-year PhD student from UIUC, and he wants to shout out that his interests are in cross-layer optimization for the cloud, network verification, and fault localization, and he wants to talk to people who have the same interests. And the paper he's going to present is Switchboard, Efficient Resource Management for Conferencing Services.
Hi everyone. I'll be presenting Switchboard, which is an efficient resource management framework for conferencing services. This work was done along with some amazing colleagues while I was at Microsoft Research India. All of us love to meet and talk, and over time, a lot of these meetings are done over services like Microsoft Teams, Google Meet, and Zoom. More meetings implies an increase in their operational costs, and our work attempts to make these services more efficient. Okay. Let's look at a simplified version of how a call takes place today. So when a user starts a call, Teams chooses one of many data center locations to start a media processing server, where the user then sends their media stream. All the subsequent users who join the call also send their media stream to the same server, which then mixes all the streams and then broadcasts it back. This process requires both compute and network resources, and the amount of resources required depends on where the participants are located and what kind of media is being streamed, which could be audio, video, or screen share. While these two properties are beyond the service's control, there is an impacting factor that the service does control, which is the location of the server, and this is the knob that we exploit in this work. So let's look at some factors that we want to consider while making the service more efficient. The first is resource cost, which comes from the cost of provisioning dedicated compute and network, which in turn depends on the peak usage of each data center and each link. Something to emphasize here is that large-scale services don't just use the cloud infrastructure, but also define how it's provisioned. This implies that these services cannot get resources elastically, and this is why their peak usage defines their cost. We also consider performance, and we define it as the average user-server latency of all users in a call. Now, along with the cost of provisioning resources to serve the call, we also consider the cost of provisioning redundant or backup resources for tolerating failures. Let's look at the baseline and state-of-the-art schemes which decide the media server location for each call. The first is the round-robin scheme. And here's a toy example where Teams has 3 incoming calls from different countries. And the round-robin scheme load balances them across different data centers, irrespective of where the users are coming from. Now, this even spreading of calls is great, since it results in the lowest compute peaks possible. But it inevitably ends up hosting calls in far-off data centers, for example, hosting the call from Norway users, from France users in India instead of Norway, which drives up the network peaks as well as hurts service performance. The other extreme to this is locality first, which optimizes for performance and picks the closest data center to all users. While locality helps in keeping the WAN bandwidth requirements and the latency low, but the geographic skew means that the local demand peaks will drive up the sum of compute requirements across different data centers. Now, it's easy to define a scheme that trades off between these two extremes, but we attempt to design a scheme that gets us the best of both worlds. So, while systems typically optimize for performance as their objective, we are exploring a different metric here. That is, we want to optimize for resource efficiency while guaranteeing performance and resiliency bounds. And here are the key ideas we use to achieve this objective. The first of which is to leverage the time-shifted nature of these demands. So the graph here shows the local demands coming from 3 time zone separated countries over a period of 24 hours. Now, an obvious insight is that they are time-shifted owing to the real user-facing nature of the service. And we could leverage this to time-share some resources and smoothen the resource usage peaks. Now, this idea of time-sharing resources can also reduce the backup capacity that needs to be provisioned. So similar to the previous graph, here is a toy example of 3 graphs that show the cores used in 3 different data centers over time slots T1, T2, and T3. The total cores required is the sum of peaks, that is 320. Now, let's see how much backup capacity would we need if we model tolerating failures of any one data center at a time. So if the Japan data center were to fail, we would need 100 backup cores at other data centers to serve the same demand. So the default technique would be to evenly split these 100 as backup cores across the other available data centers, that is Hong Kong and India. Now, this technique would overall require 160 backup cores across the 3 data centers. We notice 2 things here. Firstly, when Japan is at peak, both Hong Kong and India are not fully utilizing their serving cores, so we could double them up as backup cores for that time slot. Secondly, if a site has high peak demand, you want to put less backup there, because precisely when that site fails, the demand for backup will be maximum, and any backup capacity also placed in the data center will be lost. So we use these two intuitions to come up with a time-aware backup scheme, which significantly reduces our backup requirements, and it actually brings it down to 0 in this toy example. Now, the next idea is to leverage the presence of backup compute to lower the required backup network capacity. So let's take a toy example to understand how things work today. Let's say there are 2 users, A and B, who want to get on a call, and the potential server locations to host the call are India and Japan. There would be links connecting these users to both the data centers, and then there would be additional compute as well as network capacity planned to tolerate links and or data center failures. Now, let's say the call is hosted in Japan, and the link connecting A to Japan fails. The backup link simply takes over, and the service works just fine. The insight we had here was that we could leverage the presence of compute redundancy to get away with lesser network redundancy while giving the same guarantees. So the way this would work is, we start with lesser network redundancy planned than before. That is, let's say we don't plan any redundancy from A and B to Japan. But now, if a link fails from A to Japan, instead of having a backup link, instead of relying on the backup link for the same path, we now move the call itself to a different server, since we have both spare compute and network to the new server. Now, the last idea was to identify some application-specific characteristics to allow us for more flexibility in scale. I'll go over one such characteristic in detail. So while designing this system, we realized that it's infeasible to work on the scale of millions of calls. Recall that we mentioned that the resource usage of a call depends on where the participants are located and the media type they are streaming. So we use them to define a call configuration. Now, an example would be all audio calls with 2 users from India and 4 users from Japan would come under the same configuration. Calls with the same call configurations are identical. So this allows us to work with them on an aggregate level. The upside is that we have 30 times fewer call configs than calls, so it's much easier to scale. Now, we encode all these insights and optimizations into a linear program. This takes in the expected number of calls for each call configuration as input, and outputs that how those calls will be spread across the different data centers. The output could look something like this. This spread, in turn, also tells us the total resources that need to be provisioned. Now, the objective of this program is to minimize the cost of resource provisioning under the constraint bounds. The secondary objective is that under this lowest cost provisioning, we should optimize for performance of all calls. We compare Switchboard with the baseline schemes on 180 million call records over 3 months. The results presented are normalized with respect to round robin because of business confidentiality. A quick summary of the results is that we get the same compute peaks as round robin. We get even lower network peaks than locality first, which results in significant cost savings. And we do all this while still getting the same performance as locality first. We discuss these results in detail in the paper. Now, while the Switchboard scheme shows great results, there are challenges when it comes to enforcing the carefully crafted call spread outputted by the linear program in real time. We discuss these challenges and our solution in detail in the paper. I'd recommend to take a look. Now, we haven't solved everything, and Switchboard definitely has limitations and interesting open problems. We've discussed them in the paper, and I'm happy to chat about them offline. But a broader direction that comes out of this work is to, A, start considering resource efficiency as a metric to optimizing large-scale workloads, and also designing better interaction techniques between the cloud and the applications running on top of it to do better cross-layer optimizations. Thank you.
Hi, thank you. Very nice talk. Shoshovan from RISE. So I have one quick thing to ask is that the time when you mentioned about this, is this like locality, right? You have trying to choose some local server. So here, this locality is mentioned based on what? The source or the destinations of a certain Zoom call or something like that? I mean, how do you choose which one is like local here?
So you'll look at the spread of all the participants, and you'll pick the data center that is closest to them in terms of latency.
Like average over all of them?
The average latency of all users.
I see. Thank you.
Hi, next talk. This is Xinjun from Huawei Technologies. So the question is, sometimes some call may be time sensitive, right? So they have different priorities. They don't care about the cost, right? They don't really care about the time. How do you factor that in?
Sorry, what do they care about?
Yeah, how do you consider those factors? Because there are different priorities. Some call is more important than other calls.
Okay, so right now we treat all calls equally. But I'm sure if you want to prioritize different calls, if you have different tiering levels, you can accommodate them in the framework.
Okay, thanks.
Any more questions? No? Okay, let's thank our speaker again. Our last speaker for this session is Zerui Guo. Zerui is a first-year PhD from Wisconsin, and the work he's going to present is LEAD, a low-power, fast, persistent key-value store on SmartNIC JBOFs.
Thank you for the introduction. I'm Zerui, a first-year PhD student at UW Medicine, advanced professor Liu Ming. My research are mainly focused on SmartNIC assist executions and memory fabric enabled by CXL. Today, I'm excited to present our paper, LEAD, a low-power, fast, persistent key-value store over SmartNIC JBOFs. Nowadays, persistent key-value databases are widely used in data-intensive applications, such as web indexing, e-commerce platforms, and social networking. A persistent key-value store keeps its data in the form of key-value pair, where each key is uniquely associated with a value. Those key-value pairs are typically stored in durable devices like NVMe drives, so the data can survive system shutdowns or crashes. There are three operations in key-value store: get, put, and delete to retrieve, insert, and delete a key-value pair. Traditional solutions construct key-value stores using server JBOF. JBOF stands for just a bunch of flash. Servers are equipped with beefy processor, multi-channel big memory, massive I/O bandwidth, and tens of terabytes of storage capacities. Therefore, a server JBOF provides high read and write performance, but it comes with the cost of high power consumptions. In our test system, it consumes 252 watts overload. Another solution is use ultra-low power embedded nodes, which has been explored by young early pioneer systems like Fong. As shown in this figure, it uses an array of WinP nodes for serving persistent key-value requests. Those nodes are further divided into front-end server and back-end storage nodes. The front-end node takes client requests and then forwards them to the back-end storage nodes based on the key hash. The power draw of embedded node is low. For example, it's only 3.5 to 4.2 watts for a prototype Raspberry node, but the single node performance is also low. If serving requests at less than 10 gigabits per second as is designed, Phone is energy efficient. However, to match today's data center network speed, which is around 100 gigabits per second, such design will require a large number of backend nodes and network switches, which adds extra system management complexities. To make things worse, at this scale, it also consumes a similar amount of power as the server JBOF, making this solution unattractive. Recently, a new type of compute device called SmartNIC JBOF emerged on the market. It consists of ARM cores, onboard memory, 100 gigabytes network port. It also can connect to NVMe drives through PCIe root complex. SmartNIC combines the benefit of server JBOF and embedded nodes. It provides fast networking speed and around 1600 kIOP of random read while using little power. For instance, Broadcom Sitting Gray used in our testbed only consumed 45 to 53 watts with 4 SSD on board. Additionally, it's also cost efficient. SmartNIC JBOFs only cost 1/3 of the price compared to a server with similar configurations. However, the key issue of building key-value store on this platform is extremely architecturally imbalanced. From the memory perspective, the memory of an embedded node is only 16 times larger than its storage capacities, and 64 times for the server JBOF. However, if it's over 1,000 times in the SmartNIC case, which makes indexing value very challenging. For example, to index a 256 bytes value on embedded node, we have 16 bytes of memory available. However, we have to fit in the memory index for a key within 2 bits in our system. The second challenge is in terms of computing headroom. With high network and the storage bandwidth available on SmartNIC JBOF, a WinP ARM core needs to drive over 12 gigabits networking traffic and handle 500,000 storage requests per second to fully exploit its potential. This is significantly higher I/O density than both the embedded node case and the server case. The third challenge is uneven load distribution. This can be modeled as balls into bins problem. A JBOF holds much larger data storage capacity than an embedded node, so it requires fewer nodes, where each node would absorb a much higher maximum load than embedded case. To address those challenges, we propose LEAD, a low-power, distributed, and fast persist key-value store over a SmartNIC JBOF cluster. Our system keeps the following goals in mind. First, it needs to be fast under different access pattern. Second, it needs to be fully utilize all the SSD. Last but not least, it has to be available under node failures. To achieve our goals, we apply the following design principle all over in our system. The principle one is to treat SFIO bandwidth for scarce compute resource and memory capacities. This inevitably adds some latency, but increases the overall performance. The second principle is to make scheduling decisions as early as possible to streamline the execution flow of the request. This approach will distribute a right amount of requests to each JBOF and its core, avoiding unnecessary I/O stalls. Here is an overview of our proposed techniques. The first technique is circular log and a hybrid index. A circular log is a continuous space on SSD, pointed by head and tail pointer. We further separate the keys and the value to their corresponding logs. Inside a key log, there are segments. A segment consists one or more buckets where the keys are stored. The offset of the segments are stored in the segment table, which can be indexed by the key hash. We only put segment table in the memory. With this hybrid index scheme, we are able to index the key using around 2 bits of memory. However, this approach comes with its own downside. A get will generate 2 SSD assigns, one for the segment, another for the value. There is where we treat SSD bandwidth for memory capacities. Similarly, put will request 3 SS and delete will require another 2 SS. We also develop batched compaction to free up key and value log for future requests. To address the small computing headroom issue, we propose the second technique, which is an end-to-end token-based request scheduler. To make sure every core in our system won't override by request, we want to make scheduling decisions as early as possible. We first generate a token based on the condition of the SSD. Then according to the token, the scheduler will move requests from the waiting queue to the active queue. Furthermore, the token static will be piggybacked to the client side, which may delay further requests if there is a potential overload happening on the SmartNIC side. We use data swapping and enhance the chain replication protocol to solve uneven load distribution. The imbalanced write can be solved within one JBOF. Based on the token statics, the data swapping mechanism is able to monitor the workload between SSDs. If there is an uneven load, the mechanism will swap data to another SSD which has less traffic. We solve the imbalance rate at the cluster level. LEAD employs chain replication with request shipping to provide high availability. We enable all replicas to serve GET requests, which alleviates the uneven reads problem. If the bit associated with the key is set, the request will be forwarded to the tail node in order to get the correct value. We set up for the following 3 test beds for evaluation and generate workloads using YCSB. Here, we mainly discuss the energy efficiency benefit of our system. The y-axis is energy efficient in terms of key query per joules. The x-axis is 6 types of YCSB workloads. LEAD outperformed KeyVal by 4.2 times because SmartNIC JBOFs consume a little power than the server. LEAD achieved almost 18 times higher query per joule than phone thanks to its high performance. Please refer to a paper for other evaluations from different perspectives. In conclusion, SmartNIC JBOFs are emerging low-power, high-performance, but extremely architecturally imbalanced storage platforms. We built LEAD, a low-power, distributed, and fast persistent key-value store over SmartNIC JBOFs. The source code of the LEAD can be found on GitHub. Thanks. I'm ready to take any question.
Hi, thank you for your work. I'm Roman from Huawei Technologies. What kind of real-world use cases and scenarios do you see for this SmartNIC JBOFs?
We built this server side only using SmartNIC JBOFs, so it can replace the traditional key value store in the data center.
Hey there, Mircha from Arista Networks over here. How does this compare with in-network key value storage techniques?
You mean the switches-based key value stores?
Yes.
You still need to put SSD in somewhere, right? If you use a switch to forward the key value request. This is like a dedicated device, and it can contain the SmartNIC, the NVMe drives within this box. So I think, but I'm not very familiar with the networks edge case, so I don't sure about its power consumptions. But I think it's comparable to those solutions.
Do we have any more questions? Okay, let's thank our speaker again. And have all the speakers on stage. Do you have questions for each other, or?
I have a quick question for Switchboard. I think this is a really interesting optimization problem. So I'm just curious, in real-world deployment, what's the granularity of the change decisions made? And what's the cost of the changes? Because I'm assuming if in the middle of a Zoom call, you decide there's a change, that would affect the user performance for a little while.
Right. So we did not. That's one of the challenges, that when you try to minimize the number of changes that need to be made, and we discuss this in the paper in detail. What we do is we start off with a default heuristic on where to place the server, and after 5 minutes into the call, which is enough time up for about 80% of the users to actually join, we reevaluate if the call needs to be migrated, or if we can just do a simple accounting operation and leave the call hosted where it was.
I also have a question for Switchboard.
Okay.
With the records of Microsoft Teams, an idle provisioning can be obtained, and I wonder how far is Switchboard from the idle provisioning?
Switchboard is the ideal provisioning. Switchboard is the lowest you can provision, the lowest resource cost that you'll have to pay for provisioning, while still having performance and resiliency.
Okay.
Yeah.
I have a question for you. From the first paper, I learned LRU is the default cache policies. So why you choose the frequency instead of the timestamp as your input of the model?
Yeah, sure. Thanks for the question. So, as I mentioned, our policy prediction knobs, and indeed, then that means our whole algorithm can apply to any decision knobs. And LRU is an eviction policy. So what we're doing is an omission policy, deciding what is coming in the cache instead of what is going out of the cache. And so a common policy is just based on frequency and size. But then recency, as we actually in our paper, we have some evaluations including recency as our feature. So, but it can our technique can be applied to any set of decision knobs, including recency. Thank you.
Okay. About this question, I have my opinion. So, in the switch data plane, the packet processing speed is consistent. So the cache entry insert and evicted is at the constant cost. But in Darwin's scenario, I think that the entry replacement is its performance is dependent on the desk performance. So maybe LRU is not so suitable for these scenarios.
Oh, actually, we are using LRU as our eviction policies.
Hi, thank you. So, Shushaban from RISE. So I have a very general thing to ask to like all of you based on the theme. So the theme is to offload, right? So nowadays we know like there are several things like P4 switches, SmartNIC, maybe tomorrow some kind of other hardwares can come to like offload. So like I have seen papers who kind of do the same task to offload on P4 switch. Some other paper is doing the same task to offload on like SmartNIC. So like what do you think? What would be the next step? Maybe to offload it into all, but in a more balanced way, just to consider their constraints and advantages? Thank you.
I guess I'm not doing any offloading, so I'll let the others answer this question.
Yeah, some offloading people, please.
That's a great segue to our next session, offloading, which starts in 15 minutes.
Oh, I'm so sorry. sorry.